So now let's talk about memory protection, or some of the details about how we use virtual memory to prevent programs corrupting each other. So we saw this example before. If each program has its own page table, then we can match each program's virtual addresses to unique physical addresses, and it prevents them from accessing each other's data. So here's program 1 has its own page table or map here, program 2 has its own, and we saw how if program 1 tries to access virtual address 1024, its page table is going to send it somewhere else, maybe physical address 1 here. Program 2 also tries to access virtual address 1024, but its mapping, its page table, sends it to physical address 5, and these two things don't overlap. So let's take a look at this in a little more detail. So here's what the program address space looks like for a 32-bit Linux program. So each program has its own 32-bit address space, so each program sees the same 32-bit address space. Now, Linux defines how we use this address space. So the top 1 gigabyte of this address space is reserved for the kernel. So this is space that the program is not allowed to access, and it's for the kernel to store its data there. So the program can't read or write here, and in fact, if your program tries to access this, it'll crash. Then we have the stack. So the stack starts in here in the memory, and it's going to grow down. So the stack grows down as it gets bigger. Now remember, we used the stack when we were doing procedure calls. The stack is where you were storing registers, so you decrement the stack and it would grow down. This is where the stack is stored in memory. Then we have libraries in the middle here. These libraries are the shared data that we might have when we share with other programs. For example, if you have a save dialog box that's used by a lot of programs, it would be stored here. Then we have the heap. The heap is where the program allocates data. So if you're going to load a large image, the program is going to allocate a lot of memory on the heap. And the heap grows up. So when the stack grows down, and if it crashes into the libraries, or if the heap grows up and crashes into the libraries, that means you've run out of memory. So in addition to this here, we have two segments down at the bottom called the data and text. So the data segment here, this is the constants and data that your program has, and the text is the actual program. So this is the program code down here, or the program binary. And then finally at the bottom here, we have about 128 megabytes around 0 that are reserved basically for I/O, and the kernel doesn't let you get access to. So a bunch of space that's reserved for the kernel. We have the stack that goes down, the heap that goes up, libraries in the middle, and then we have our code and data for the program in the bottom here. There's something else that Linux does that's pretty cool. It puts random offsets in here. So your stack doesn't begin right at the end of kernel space. There's some random amount of space that's just wasted here. Then there's some random amount of space between the stack and the libraries, and some random amount of space between the data and the heap. And the reason for this is for security. So these offsets enhance security because you never know where your data or code is. So if I'm going to try and hack this program, so I'm going to try and write some data into it that makes it do something different, well, I need to write this down here in the actual part of the program that executes code. But if I'm up here somewhere in the stack and I've got this random offset, it may be hard for me to find that down there. Or if I want to write some code into the stack and then rely on something jumping back to it, well, if I don't know exactly where the stack is, it's hard for me to figure out where that jump is. So these random offsets here help reduce a bunch of different attacks that you can make on the program and improve security. So let's take a look at how these address spaces overlap in Linux. So here's two programs, program 1 and program 2, and they both have the same view of the address space. This is their own 32-bit virtual address space. And you can see how they map. So the kernel space in both of these maps to the same place in physical memory. That's fine. They're neither of them allowed to access it. Here in this case we have the stack for program 1 mapping into here. We have some of its libraries mapping into here. We have the heap from this program mapping into here. And maybe its libraries are mapping partially into here, so shared with the libraries from program 1, and some of its other libraries are down here. And so by doing this, we can use our mappings, or our page tables here, to allow these two programs to have the same view of their private virtual address space, but share the physical address space in a secure way. So here they can both share these shared libraries, but the stack for this program up here is not accessible from program 2's address space because it has no page table entry which will get it to this location. So we have these separate mappings that allow us to keep programs isolated, but we can also use these mappings to share data, as we showed here. So how do we provide these separate mappings? Well, the operating systems make sure you use the right page tables. So we have two programs here. They're both going to do a load to some location here, address 2 in this case, so virtual address 2 from both of these. They're both going to have their own page tables. They're both going to look up where virtual address 2 points to. They're going to get two different physical page numbers. So this one got a physical page address 4, it's going to find it over here, and this one got 9, it's going to find it over here. So they go ahead and access their data, and neither one of them is going to conflict because they get mapped somewhere else. And in fact, if you look through these page tables, you can see exactly how they're sharing the memory. So program 1 has physical page 1, 3, 4, and 6, so it gets 1, 3, 4, and 6. Program 2 has physical pages 5, 8, 9, and 2. So here's 2, 5, 8, and 9. It gets those ones. And both of these programs share physical page E. You can see that they both map virtual address FFFFF to physical address E. So that's the shared page down here. Now here's a question. I have two programs, and here are their page tables. And so which pages could these two programs access that would allow them to corrupt each other's data? Well, in this case, program 1 can access virtual page 2, which will go to physical page 4, and program 2 can access virtual page 1, which will also go to physical page 4. So in this case, these virtual addresses map to the same physical page. So these two programs could both access the same physical page, and they could corrupt each other's data. Or this data could be here because they need to communicate with each other. Think about if you're copying and pasting from one program to another. They have to be able to share that data somehow.